Hello there, and welcome back to another learning series with Mr. Knight. Today, I am continuing with covalent bonding, but as promised, I'm going to use different non-metals. For this lesson, I want you to put on your chemistry seatbelt. I'm going to take you for a ride. By the end of this lesson, you should be able to draw structures like this and also name simple covalent compounds. Before I get into the examples, I'm going to remind you what covalent bonding is. Then I'm going to outline 3 things you need to know to do this type of bonding. So covalent bonding involves the sharing of valence electrons between non-metals. For this type of bonding, the 3 things you need to know include 1, the number of valence electrons of each atom. You also need to know the amount of electrons needed to achieve an octet. Also important to know is the number of each atom needed for the bonding. Now let's look at our examples. The first example is hydrogen and oxygen. Now this outline that I'm presenting is for you to use to prevent any mistake and to make it very easy. This outline is applicable to simple covalent compounds. So this is when you're doing simple covalent compounds. Now let's jump into it. Hydrogen has 1 electron. Hydrogen is a special atom in that its first shell is also its last shell. Therefore means that that shell can only contain a maximum of 2 electrons. Therefore, to achieve a full or stable shell, there can only be 2 electrons on that shell. Oxygen has 8 electrons. Therefore, the electron configuration is 2 and 6. Therefore, means that the valence electron is 6. Now let's put on our valence electron. For hydrogen is 1 and for oxygen is 6. Now remember that hydrogen can only take on 1 more electron because the first shell is also the last shell. So the number of electrons needed by hydrogen to create a full shell is 1. The number of electrons required by oxygen to complete that last shell or to create that octet is 2. Now the number of atoms needed, or at least the number of atoms for each, to obtain this part, it is kind of a special. First, what you have to do is to cross multiply the number of electrons needed by each atom. So I'm going to cross multiply. And so therefore means to create this bond, you will need 2 atoms of hydrogen and 1 atom of oxygen. Very important to point out this is that the number of atoms needed should be in the lowest possible whole number ratio. 1 and 2 is the lowest number. Alright, so remember now, to draw the number of hydrogen, you require 2 atoms, and for oxygen, there is only 1 atom. So let's go into the drawing process. Alright, I'm leaving this here to remind us what we're going to do. Now, the first thing you want to do is to draw the atom with the lowest number, and in this case, it is oxygen. So you want to draw the structure of oxygen first. Then attach to that 1 atom, you're going to put your 2 hydrogen, because remember, hydrogen is being bonded to oxygen. So once you draw your circles representing your atoms, it is time to put the number of electrons in the bonding section. The way you're going to do that, or determine the number of electrons to put in these sections, is simply to look at the lowest number of electron needed. So in this case, the lowest number of electron needed is 1. So notice the statement, the number of electrons contributing to the bond from each atom, you use the lowest number of electron needed. But in this case, each atom must give up 1 electron. So let's start right here. So oxygen will give up 1 of its valence electron to the bonding. Also, hydrogen will give up 1. So notice that blue for hydrogen in this case and red is for oxygen in this case. And I'm only using different colors to prevent any mistake and for you to follow quite easily. So on this section, oxygen will also give up 1, and also hydrogen must give up 1. Because remember, all electrons must be in pairs, whether bonding or lone pairs. Now, we established these. Now the next step is to put on the remaining valence electrons. Now let's start with oxygen. Oxygen gave up 2 valence electrons from its 6. So the remaining portion of valence electrons will be 4. So let's put on those 4 valence electrons. Notice these are lone pairs. All right, let's look at hydrogen if there are any other valence electrons remaining. Hydrogen has only 1. It gave up its 1, so there's none remaining on the outside. Now, once you have done that, you need to check to make sure that each orbital or shell is completely full or satisfied. So let's look at oxygen. Around the orbital of oxygen is 2, 4, 6, and 8. So oxygen is completely filled, or at least create that octet. Let's look at hydrogen. And remember that hydrogen is special in that it only requires 2 electrons. So the 2 electrons are here for this orbital. So this hydrogen is completely satisfied. Let's look at this one. There are 2 electrons right here. So this hydrogen is completely satisfied. So this bond is completed. So now we can draw a structure. So we require 1 atom of oxygen and 2 atoms of hydrogen to create water. So this was kind of fun and easy. So let's do some more examples by following the outline. Our next example here is carbon and fluorine. First thing to establish is the number of valence electrons. So carbon has 6 electrons. The electron configuration is 2 and 4. For fluorine, contains 9 electrons. Therefore, electron configuration is 2 and 7. So the number of valence electron for carbon is 4. The valence electron for fluorine is 7. Remember, we're going to create an octet, which means a full shell, maximum of 8 electrons. And so the amount of electrons needed to make this 8 will be 4 for carbon and only 1 for fluorine. Now remember, to determine the number of atoms is to cross multiply the number of electrons needed. So just cross multiply those. And what you get in this case is 1 atom of carbon and 4 atoms of fluorine. Now we're looking for the lowest possible whole number ratio. And of course, 1 to 4 cannot go any lower. So we're good at that. And so we can jump into our drawing process. So once again, to remind you what we're working with, carbon, 1 atom, and fluorine, 4 atoms. Always draw the lowest atom first. So we're going to draw carbon first. And so the atom of carbon, you draw only the lines without the electrons. And attaches to this carbon will be 4 atoms of fluorine. Remember, fluorine is not bonding to fluorine. Fluorine is bonding to carbon. So all fluorine atoms must be attached to carbon. So once you draw that, the next step is determining the number of electrons that will be going into the bonding section. Now, the way to do that, again, to remind you, is looking at the lowest number of electrons needed. So in this case, it is 1. So each atom will contribute 1 valence electron to the bonding section. So notice, let's start. We could start anywhere, it doesn't matter, but let's jump into it from this side. Carbon will give up 1. Likewise, fluorine will give up 1. In the other section right here, carbon give up 1, fluorine will also give up 1. In the other one, remember we only work with number 1, okay? Each atom. So in the next section, carbon will give up 1, fluorine will give up 1. In the next section, carbon is given 1, fluorine is also given 1. Now the thing now you're going to do after you completed the bonding section is look at the number of electrons remaining. Carbon has 4 valence electrons. It gave up 1 here, 1 here, 1 here, 1 here. So on carbon there is none remaining because it gave up all its valence electron, 1 in each section. Now let's check our fluorine. Fluorine only gave up 1, but fluorine has 7. So it gave up 1 from the 7. Therefore, on each fluorine will remain 6 valence electrons. So we're going to put the 6 valence electron on this one. Also go to the next one and put on the 6 remaining from the 7. Also going to go to this. Remember, it gave up 1. So 6 remaining from its 7. Again, it gave up 1. So 6 remaining from its 7 valence electron. And once you have done that, the bonding is completed. Now what you can do is to check to make sure the numbers are correct. Each orbital should have 8 valence electrons. So around carbon is 2, 4, 6, and 8. So carbon is completely satisfied or filled. For this fluorine is 2, 4, 6, 8. Again, around this fluorine is also 2, 4, 6, and 8. This one will also be 2, 4, 6, and 8. Around this fluorine will be 2, 4, 6, and 8. So all the atoms are completely satisfied or completely filled. Now, based on this structure, remember what these are. Single pair of electrons create a single bond. So this molecule will look like this. 1 carbon, single bonded to 4 fluorine atoms. And so the name of this molecule or compound will be carbon tetrafluoride. Easy to name because tetra means 4, which means 4 fluorine atoms. So 1 carbon atom to 4 fluorine atoms. Or it can name, as the IUPAC name, is tetrafluoro, which means 4 fluorine methane. So the methane comes from 1 carbon. So the tetra means 4, fluoro coming from fluorine, and methane means 1 carbon. All right, so now we finish with this example. We can jump into another example, and this example will be very interesting. Okay, so now we're in the example, and we're going to do sulfur and oxygen. Now, this one will be a nice one, I promise you. Now, first to establish is our valence electrons. And so sulfur has 16 electrons. Therefore, the electron configuration is 2, 8, and 6. For oxygen, 8 electrons, electron configuration 2 and 6. Therefore, the valence electrons for sulfur is 6. And the valence electron for oxygen is 6. Now, I'm going to point out something right here because this is also a good way to look at it. If the atoms or elements are from the same group, you only need 2 circles. or 2 atoms, which mean 1 atom each. So I will show you at the end and you're going to see. Once they are from the same group, you only require 1 of each atom. But I'm going to go through this process just to keep the trend of what I'm doing, but you could make this shorter once they have the same number of valence electron. So you're going to see that at the end, however. So the amount of electrons needed by sulfur to make this complete, which you're working to achieve 8, is 2. For this other one, again, is 6, so therefore it requires 2 more to become 8 or create that octet. The number of atoms needed, again, remember we cross multiply, so we cross multiplying here. And notice the numbers at the bottom. The number of atoms of sulfur requiring here is 2. That of oxygen is 2. But notice the statement, we are working to achieve the lowest possible whole number ratio. 2 and 2 is not the smallest possible whole number ratio. It can become lower. So what we can do here to make it lower is divide both sides by 2. If we divide both sides by 2, you notice you get 1 each. As I mentioned, you can look out for this. Once the number of valence electrons are the same, you know you're going to need only 1 of each atom. All right, so that's the next rule you can look at. All right, so let's go into our drawing segment. And so again, this is to remind you what we're working with. Sulfur 1 and oxygen 1. So all you need to do is to draw 2 overlapping rings or orbitals, 1 for sulfur, 1 for oxygen. Now the number of electrons that will be placing inside of the bonding section depending on the lowest number of electrons needed. But in this case, the numbers are the same, so it doesn't matter. Each atom must give up 2 electrons each. So in this section, sulfur will give up 2. Oxygen will also give up 2. Now time is to check the amount of remaining valence electron. So for sulfur, we gave up 2 out of its 6. So how many remaining? Likewise, for oxygen, we gave up 2 out of its 6. So the amount of valence electron remaining here will be what? 4. Because remember, it started out with 6 valence electrons. You gave up only 2. For oxygen, the similar thing. It gave up 2 out of its 6, remaining 4. Now, let us check to see if each orbital achieve that octet. So around sulfur, there are 4 electrons here, 6 and 8. So that is completely satisfied. Around oxygen, 4 electrons, 6 and 8. So this is completely satisfied, both of the atoms. So the structures here, I want you to notice inside of the bonding section, there are 2 pairs of bonding electrons. And remember, 2 pairs of bonding electron give you a what? Double bond. All right. So sulfur bonding to oxygen gives you a what? A double bond. So the name of this compound is sulfur monoxide, which means 1 oxygen. All right. And so the structure is that. And now this is completed. We can jump into another example, which will be our last example. And this one will also be a very interesting one as well. So let's go into it. Now we're bonding carbon and oxygen. Oxygen is very diverse in bonding covalent compound, by the way. Carbon and oxygen, they're very diverse, especially carbon. All right, in the next lesson we'll talk about that. But let's jump into this right away. Carbon has 6 electrons. Therefore, the electron configuration is 2 and 4. Oxygen has 8. Therefore, electron configuration is 2 and 6. So the number of valence electron for carbon is 4. That of oxygen is 6. The number of electrons needed by carbon to complete that octet will be 4. The number of electrons needed by oxygen to complete that octet will be 2. Because remember, you're working to achieve 8. Now, to get the number of atoms required, we cross multiply. And so there will be 4 and 2. So 2 for carbon when you cross multiply, and 4 for oxygen. Is this the lowest possible whole number ratio? No, because they are multiple. Okay, so what we're going to do now, we can divide both sides by 2. So make this the lowest number. 2 divided by 2 gives you 1. 4 divided by 2 gives you 2. So to make this structure, we require 1 atom of carbon and 2 atoms of oxygen. So let's go into a drawing segment. Again, to remind you what we're working with, we draw 1 carbon atom, so always draw the lowest one first. So we draw that 1 atom of carbon, and attaches to this 1 atom of carbon will be 2 atoms of oxygen. So let's draw our 2 oxygen atoms. All right, draw them on either side. And then the next thing is to determine the number of electrons go into the bonding section. Remember, what you do to that is to look for the lowest number of electrons needed. So each atom must contribute 2 electrons to the bonding section. So let's go into it. So we could start with carbon giving up 2. If carbon give up 2, oxygen must also give up 2, because it must be from what? Each. Okay, then go into the next section here. Carbon will give up 2. Oxygen will also give up 2. And so once we complete the bonding section, we can now put the remaining valence electrons on the outside. But let's check for carbon first. Carbon gave up 2 electrons here, 2 electrons right here, making it 4 electrons. Carbon only has 4 valence electrons, therefore there are no more remaining valence electrons. So for carbon is completely good. Now for oxygen, oxygen started out with 6 valence electrons. It gave up 2, so therefore the remaining portion here will be what? 4. All right. Now look at the other oxygen. It gave up 2 out of its 6, so therefore there are 4 remaining. And now we could check to make sure that each orbital is completely satisfied. So for carbon, you have 4 electrons here and 4 electrons here, making it 8 for carbon. So carbon is good. For this oxygen, there are 4 electrons here, 2 here, 6, and 2 more here, 8. So that is completely good. On this side, there are 4 electrons here, 2 here, and 2 here, making it 8. So all the orbitals are completely filled. Now, therefore, notice here that, again, 2 pairs of bonding electrons make a double bond. So there's a double bond here. 2 pairs of bonding electrons again make it a double bond on this side as well. So the structure will be oxygen to carbon, a double bond, and here will also be a double bond. And this is carbon dioxide. This is what we will excrete when we respire. And plant also need carbon dioxide for photosynthesis to produce energy and food for us. All right, so this is the structure here. And so, my friends and students, it was a great pleasure to be here with you to demonstrate these scientific methods and also these series. And so I'm saying to you, keep safe, and I am definitely looking forward to see you in the next lesson. Keep safe.